And I'm live. That is pretty cool. Today is 3rd of February 2026, Tuesday, and with that, let's start. Yep. And today we will be reading about directed graphs. Yep. From the CEP handbook, Competitive Programmer Handbook. In this chapter, we focus on two classes of directed graphs. Yesterday, we saw what uh, two algorithms for finding out minimum spanning tree. What is a minimum spanning tree? And the new thing that I said that we saw was a data structure, implementation of a data structure, which gives us two abilities. And one of them is checking if two nodes belong to the same component in a graph or not. And the other is to join two components of a given graph. And both of these functions work in log n time, which is pretty cool compared to some naive approaches. And the data structure is called this union find structure. And we also wrote a implementation for the same thing. Data structures, we wrote a class for this thing. Class would be called union find class. Yeah, and that is pretty cool. This has a few functions. This is constructor, same, checking if two nodes are in the same component or not, and unite to add two components together, and print to just print these underlying structures which hold the whole thing together, which describe the whole structure. And yep, again, like this thing actually happens every day. Caps lock should act as control for the USB keyboard. Yes, cool. And for now, we are moving on to directed graphs. What are directed graphs? Let's see. In this chapter, we focus on two classes of directed graphs, acyclic, cyclic. There are no cycles in the graph, so there is no path from any node to itself. Okay, no cycles. And then successor graphs. The out degree of each node is 1, so each node has a unique successor. Okay, that is new. That is new. Acyclic is like common. People know about acyclic. There are no cycles in the graph. But successor graph is a graph, the out degree of where the out degree of each node is 1. So each node has a unique successor. Okay, that is cool. So, wait, shit. Where is the content here? So like uh, since this is directed graph, they are saying for each node there is only one new node that the previous node points to. Every node only has one out pointing arrow pointing to another node. It is not like this. Like here, this node has two outside arrows. In a successor graph, every node has a single out pointing arrow. Okay. It turns out that in both cases, we can design efficient algorithms that are based on the special properties of the graphs. But what do we want to do with this? This is just what the data structure looks like, but not, this does not tell us what we want to do with it. Let's see. Topological sorting. That might be one thing that we want to do with our graphs. Okay, a topological sort is an ordering of the nodes of a directed graph such that if there is a path from node A to node B, then node A appears before node B in the ordering. For example, in this graph. Okay, since there is no cycle, makes sense. Since there is no cycle, then for any path from one node to other, we will have nodes which come before and we will have nodes which come after. Since there is no cycle, if there was a cycle, then we would have something circular and we would not be able to say which thing comes first and which thing comes later. So yep, we do not have a cycle, and therefore we have nodes which come first and nodes which come later on. therefore, in a topological sort, we want to sort each node in such a way that for each path that we might have in our graph, the nodes which come before or earlier in the path are placed earlier, and then the nodes which come later on are placed later on. Here 4 comes first, and then 1 comes, and then 5, and then from 5 we have 2 and 3 come later on, 2 and 3, and then 6 comes the last. Okay, that is cool. For example, this is a topological sort. And how would we go about achieving this thing, topological sort? Topological sort, how do we go about achieving this? So our topological sort will begin, I think we can just apply a BFS, and our starting node would be a node which does not have any other node pointing to it. So for example, here we have 4 and no other node is pointing to 4, and then we can go by BFS layer by layer. Yeah, we can just go using BFS layer by layer and keep adding stuff to our this thing here. So let's implement topological sort. Top dot ppp nonsense namespace std, yep, and main, and we will have our vector of vectors, yep, adjacency list, yep. Okay, and let's have our topological sort. It will return a list of vectors, a list of integers, the nodes in their topological order, and we'll call it topology. And this simply takes in the adjacency list, and I think adjacency list is a nice way to describe the data structure here. And after this, we have to find a node which does not have any other node pointing to it. Yep. And since we are using a adjacency list, for this we will have to go through each edge. Yes, we will have to go through each edge. Vector boolean mm, in, and size would be adj dot size -1, or adj dot size makes sense. Everything is initially false, and we will say in I equal false means no other node points to this one, and true means other node does point to this one, and in 0 will just become true just in case. And then we will go through each edge for auto v adj, and for auto x n v, look, in x equals true, x is pointed to by some node. Okay, and then we will go through the in vector and find out the Find out the node which is not being pointed to by anything. So auto it equals in dot, okay, find if in dot begin and in dot end. And what are we looking for? Bool x, return not x. If this is, we are looking for something that is false. Yep. And we would like to have its index. Yep, we would like to have its index. So minus n dot begin and star is this, and then vector bool response size would be adj dot size, or we can just have a ref and then this dot insert start. Okay, insert is not the thing. Push back start, and now we will start our BFS. Q of integers. I think we can here say vector, and yeah, that does work. Q dot push start, and we also need a visited array. Vector pool visited size would be adj dot size, and everything would be false initially. And yeah, while q, while not q dot empty. And also at this point we will say visited start equals true. Okay, in C current node equals q dot front, and then q dot pop to remove this thing from the front. And then we will go through every node that is connected to this node for int x in adj c if not visited x, if x has not been visited, visited x equals true. Rest or push back x, push back x, and q dot push x. I think that is good enough. And then return. Okay, yes, do not return res. Quick start, and cool, that should work hopefully. Hello. Yep, doing graph siphon, and we are currently doing topological sort. What is topological sort? And we are using BFS here, which looks like the only way, and I am predicting that they are also going to tell us the same thing. And DAG, directed acyclic graphs, directed acyclic graphs. Cool. Then comes the algorithm. Now let's use the same graph, use our algorithm on this graph. Shit, sound is low. Bro, I have done with this graph. Yes, we did do this graph at some point. Today I tried solving a problem that, wait, I thought you do solve problem, and that is like your normal routine. Extended Dijkra. What is that? Maybe some variation to the basic Dijkra, and sound is low. Um, it is from my side like full blown, it cannot be greater than it is right now. So yeah, like we add extra n. And this, can you send the problem? Let's see if we can solve that. And yep, here 0, nothing is connected to node 0. Node 1 points to node 2 and nothing else. And node, this is node 1. Node 2 points to node 3 just and nothing else. And node 3 just points to node 6. Shit. So node 6 and node 4 points to 1 and 5, and node 5 points to node 2 and 3, and then 6 does not point to anything else. Like, yeah, 6 doesn't point to anything. Cool, we have our data. We just have to call the function topology auto response, or something more fancy, topologically sorted. Topology, give it ADJ, adjacency list, and see out topologically sorted. Compile and error. Now error. C dot pop front is C empty. C dot pop front has no member pop front. We are only doing pop here, but Q is a queue, so there should be a member called pop. Then maybe we should not tell it the underlying data structure. Okay, cool. And we get 4 1 5 2 3 6. 4 1 5 2 3 6. Cool, that worked. Add coders beginner contest problem E. This I started watching Vyro playlist and until installation of Lazy. Yep, Vyro is cool. Vyro is cool. This one. Okay, let's like after this in a while. Cool. So topological sort works. Pretty cool. And would I like to add this to my new Vim configuration so that this is available? Add contest, maybe, I don't know. Okay. An acyclic graph always has a topological sort. Yes, because if there is a cycle, then we won't be able to topologically sort the thing, because there would be no starting point and no end point. Like this, like this. Okay. However, if the graph contains a cycle, it is not possible to form a topological sort. Yes, same point. Because no node of the cycle can appear before the other, because there is cycle. The nodes of the cycle in the ordering. It turns out that the DFS search can be used to both check if a directed graph contains a cycle, and if it does not contain a cycle, to construct a topological sort. A DFS search may tell us if there is a cycle. How would it tell us that there is a cycle? I mean, yes, we can use a DFS search to find out if there is a cycle in the graph or not, but how can we use DFS for a topological sort? Because if we were to use DFS starting from 4, let's say, then from 4 we would go to 1, to 2, let's say, then to 3, and then to 6, and then we would go to 5. But where should we put 5. We should put 5 at the same level as 1, but we do not have that information, or that information would be easily available if we were to use BFS. Let's see. Algorithm. The idea is to go through the nodes of the graph and always begin our DFS search at the current node if it has not been processed yet. Yes, during the searches, the nodes have three possible states. State 1, the node has not been processed, white. We'll call that white. Okay. Stage 2, the node is under processing, light gray, and the node has been processed. Okay, what do they mean by process? Initially, the state of each node is 0. Nothing is being processed. When a search reaches a node for the first time, its state becomes 1. Finally, after all successors of the node have been processed, its state becomes 1. Its state becomes 2. When all the successors of the nodes have been of that particular node have been processed. Okay. Okay, so they have three states. Makes sense. Unprocessed, being processed, completely processed. If the graph contains a cycle, we will find this out during the search, because sooner or later we will arrive at a node whose state is 1, which is being processed, and we have reached that processed node. In this case, it is not possible to construct a topological sort. Makes sense. If the graph does not contain a cycle, we can construct a topological sort by adding each node to a list when the state of the node becomes 2. Makes sense. This list in reverse order is a topological sort. In reverse order, yes. Not processed, not processed, being processed, being processed, being processed, and also being processed. Now 6 has been processed, so it is added to the list. After this, also nodes 3, 2 are added to the list, because 6 is processed like before any other node, because 6 does not have anything else going from 6 to anything else. So yes, it is processed, and 3 only points to 6, which is processed. Therefore 3 is also processed, and 2 is also processed because it only points to 3, and same for 1. And then we move on to 5, I guess. 5, yes, 5 will be processed. And now since 1 and 5 are processed, 4 is also considered processed. Yep, we get something like this. We reverse the whole thing and we have our answer. But how do they write this in terms of an algorithm? Note that a topological sort is not unique, and there can be several topological sorts for a graph, and we do not have to use their algorithm for this. I think this one is simpler. We are just using a BFS from a node, starting with a node that does not have any in pointing nodes. Yep. Example 2, let us now consider a graph for which we cannot construct a topological sort because the graph contains a cycle. A graph like this, there is a cycle. Where is the cycle? There are multiple cycles. This one, 2 to 3 to 5, and then 1 to 2 to 3, 5, and no, shit, this is the only cycle. 2, 3, and 5. Yep, yep, that is the only cycle. 2, 3, and 5. The search proceeds as follows, and we reach 5 again, which is being processed. Yep. The search reaches node 2, whose state is 1, which means that the graph contains a cycle. In this example, there is cycle this. Okay, so we have not in our code written a check to check if there is a cycle or not in the whole graph. Let's do that also. Checking for a cycle. And I guess, should we write a class for this? No. Functions seem better here. Yeah, class is better. Class is better because in a class we can at least declare all the functions at one point and then use all of them whenever wherever we want and declare them later on. Yeah. So class algorithm. Okay, and so this is what I want to do now. There is this data structures thing. I want to write two classes, one for algorithms and one for data structure. And yep, and just add them in my new Vim configuration so that they are available at the time of our contest. Okay, I will do a separate string for this. This can be big. Sorting all of these functions where they will go. Data structures, boilerplate, CSES boilerplate, uh, a Diophantine equation. Yep, and function for finding the modular inverse. That is cool. Policy-based data structure. This will not be a class. This is just like header file declaration. Power function, finding primes, sieves of Eratosthenes, print vector. Yes, we would also need something like this. This thing prints a vector. Okay, what is this? Is template type. I think we say type class or class. Yep, OS output stream reference operator. This which takes in stream reference OS and a vector of type T, reference or anything. We'll call it V. And if V dot size, if V does have elements, then we will print them. But if V dot size is 0, then we will say not cout but OS will take in just empty thing and also a new line else and then return OS. Yep, and here first of all OS takes in a single opening bracket and then for auto whatever the type of the elements in V are cout OS not OS OS takes in X with a comma no, using index would be better. For int equals 0, I is smaller than V dot size I plus plus. Output stream takes in Vi and if this gives a comma or a closing bracket depending on if V equals I equals V dot size minus 1. Return once. That is good enough. Tom.cpp and here this is the current, this was how the code was before, and this is how it looks now. No, yep, and this still works. Okay, now we want to add and want to write a class called algorithms which does multiple things. One public function is going to be which returns an integer. topology, topological sort, which takes in a vector, int, reference, adjacent list, and we are not going to define it here. We'll define it later. We are defining it here. Algorithms, topology is nothing. Topological sort. Yep. And we cannot call this like this. Shit. If you want to call any function of this class, we would first have to make a object of this class and call a member function of it. Maybe we can call this static. If you call this static, then this function is a part of the class instead of being a part of an object of that class. So I think we should be able to say here algorithms dot or this topological sort with ADV. This just works now. So we can call this function as part of this class, and we do not have to make a object of this class and then call the function. But I guess if we were to remove the static keyword, maybe we get error. Yes, we get an error because call to non-static member function without an object argument. So if this thing, if this function topological sort in this class called algorithms is not a static member, which it is not right now, what we have to do to call this is we will have to make a object of this class. Now we have an object, and on that object topological sort, on that object we will call the function. But if this were a static member, we can just call this directly from the class. We don't need an object like this. And what is static? Static means program storage, memory space. In a program, this is how memory is stored. At one place, there are instructions. We have heap and stack, things on the stack, things on the heap, and there is a place in the memory where we store all the constant variables and all the things which do not change during the execution of the program and are fixed. And yes, and are fixed and cannot change in size or in value. They can change in value, but they cannot change in size. They have a fixed size. Those things come in this separate location, and this location is called the static space. And that is why this function has to be static, so that this is like always present throughout the whole execution of the program. So we can just call this function. I hope that makes sense. Then I started watching. Okay, shit, I read that. Okay, you want to add one more function, static, and this will give us a bool is cyclic graph. And this also takes in an adjacency list. And this is actually pretty cool because we can here use uh, argument overloading, and we can define the same function with different types of input. Like uh, here, this is taking in adjacency list to define a graph, but we could even give it a vector of, let's say, pairs, and that would be a list of edges, and we can just call the same function with the same name, just our input type is different. So that is cool. Now onto the function. Bool is returned by algorithms is cyclic graph adjacency list. Yep. And let's say return true for now. And we will use this. We can use this algorithm which they have listed in this book, where every node has three different stages, state 1, 2, and 3. And if we ever encounter while our DFS, if we ever encounter a node which is in state 1, that means we have a cycle and shit, that is bad. Is there any other way to do the same thing? Not more optimal, but just different from this. I guess. But yes, if there is any other way to find out if there are cycles in our algorithm, that would also still require us to put nodes in more than two states. Normally, when we use DFS or BFS, nodes are in two states, either visited or not visited. But here we need three states because here this graph is not cyclic, but there are two ways to reach this node number 2. If we started at 4, then from 4 we would reach 2 like by this way, and 2 would become visited, but then we would again reach 2 from this other way. And now since we have two ways to reach 2, do we consider both of these, like do we consider this a sign that there is a cycle in the graph? So yeah, we need three states. Let's just write this algorithm. So vector of integers for states size would be adj dot size, and initially every node has state 0. Then we will use our DFS. And do we want our DFS? No, we would need different DFS algorithms for different purposes. So let's have different DFS algorithms. This doesn't return anything. DFS, yes, DFS cycle checker, and this takes in I, integer I, the current integer that we are at, and also the adjacency list, and cool. Let's write our DFS checker, cyclic checker. Okay, spelling for ADJ is wrong. That is like a three-word spelling, three character. ADJ DFS checker has these two things, and shit, it also needs a visited array. Not a visited array, but the array for the states. So vector of integer, and we could maybe make these variables global so that we don't have to pass them. But then do we define them here? I think we can define them here. I think it will be fine to define them here, maybe. Let's see. Because whenever we need a variable, we will first of all empty it and then use the same thing. And we cannot say static here. Should we can say static? Hmm, how can we cannot. Shit, that is messed up. That is messed up. How can we say static with a variable that goes on to heap? Because vector is stored on the heap. How can we say static? Because I think the container which stores the vector itself, the values of the vector that will go onto the heap, but like the pointer and metadata about the vector, like the size and everything, that will go onto the stack. So, okay, that is fine. So let's also move other data structures on there. Q, nope. Here we do not need to pass anything, so we don't have to put anything onto the stack. That is good. Let's remove. Just I would be the only requirement, and states would also go under. Okay, states is already under. Uh, Here you see vector in ADJ, but state, yes, states will be here. You will have to pass an ADJ because ADJ is something that will be given to the function by the user. Yes, you will use that same thing. Vector intent ADJ. Now the effects, okay, and for and x everything that is connected to node I, for all the outgoing nodes, there has to be something else which the DFS function will tell which is cyclic function. Okay, this does not return void, this will return bool. Return false. But if states of x equals 1, that is messed up. Return true. We got a cycle. Otherwise, if states of x equals 0, if this has not been visited yet, then states of x put it equal to 1 called DFS cyclic checker on x, and x here does not mean Twitter. Yes. Okay, and we have updated the state. That is cool. And after it has been processed, we can just say states x equals 2. That seems good enough. And if the state is 2, we don't do anything. Okay, and after this, we will call, we will go through each node. States is here. No, state dot assign size would be ADG dot size, and everything is initially 0, and for int I equals 1, I smaller than equal to ADJ dot size I plus plus not equal to ADJ dot size. And if we see if states for I is 0, or if not, states of I, if states of I is 0, that is we have not visited this thing, then we call the DFS algorithm on I and pass in the adjacency list which has been given to us by the user, and not in bool response equals false res equals res or bitwise or a normal or this, and then return res. Cool, I think that would be good. So if we call after this cout algorithms is cyclic graph and we give in our adjacency list. Let's see, this should say false or this will give us error. Undefined symbol difference from, yep, I think it is because of this states is not defined, or at least we should not use static here. Static is, yep, does not make sense. And since static does not make sense, yep, does it make sense now if we were to call this static and define this from inside a function? The problem is this variable is states has to be defined from outside the function, but we do not want the caller to define states. This would not be a problem if we were to define states here before calling this. And also shit, states is private, so no one can define it. They can define it. No, they cannot. This has to be non-private. Okay, still problem with vector int does not provide a caller operator. Expected this after. Okay, what is the error here? JS algorithms states states is static. Now it is part of a object. Shared. Okay. Instead of this vector in states variable of size, everything initially equal to 0, and then we can just pass states here, change the function signature vector integer states and remove this vector integer reference states states and let's see. Cool, 0 false because there is no cycle. And shit, there has to be new line. What's new line? 0. Cool. And instead of 0, let's print if this is true, then say true. Otherwise, say false. False. And if we were to add a cycle, how would we add a cycle to this thing? Hello. Hello world. Shit, that is some binary code there. Hello. How's this? How's everything? And yes, today we will do our thing. how do we add a cycle? We can add a cycle by changing this direction, changing the direction of this thing from 5 to 3 to 3 to 5. So 5 points to 3. Remove that and let's say 3 points to 5. Now we should say shift VC false, which is messed up. We see false, which is wrong. Why do we see false? This should be true. It's cyclic. TFS checker states, yep, I guess. Shit, yes, I'm not taking into account what is written by this thing. Yes, if this thing says true, then return true. And same thing here. Instead of like this, return false. And here, remove less. And if defect cycle checker call this on X, X return true. Why is X problematic? Because there is no X, there is I. Yep, now it does work. And let's change this back 5 points to 3. So there is no cycle and we should see false. We see false. Cool, cool. We see false. We see false. That is expected behavior. Cool. Okay, we can detect a cycle. We can topologically sort our directed graph if there is a possible way to do that. First, read the title as graphics. Nope. I thought you were starting with nope. Raylab is cool, but yes, nope. Or then I couldn't explain it earlier. I wanted to prove some of the basic functionalities directly without syscalls. Without syscalls, so I implemented a standard out and standard in built in. Okay, once standard in is implemented, which won't really take much time, it will be ready for simple programs like. But this is not a virtual machine, more like a interpreter. I will have to go through the code to say more, but yep, this seems more like a interpreter, not a virtual machine, like a writing our own assembly interpreter, taking user inputs and conditionally printing something. Yep, more like an interpreter than a virtual machine. Virtual machine would give you kernel and hardware access. This is also giving you kernel. This is not giving you a kernel. This is giving you a hardware access. Yep, and this is not talking to the processor. We are just writing our own language using language, more like how Python is written using C, something like that. An example, let us now consider a graph for which we cannot construct a topological sort like this. Yep, we read that already. And dynamic programming. How do we have dynamic programming here? If a directed graph is acyclic, yes, there is no cycle, dynamic programming can be applied to it. For what? For example, we can efficiently solve the following problems concerning paths from a starting node to an ending node. How many different paths are there from a starting node to an ending node? Okay, what is the shortest, longest path? Yes, using BFS, we can do this. And this does not matter. We can use BFS or DFS. In here also, we can use DFS. We would have, yeah, DFS would be fine here. What is the minimum maximum number of edges in a path? Same thing as this. kind of same. Here we are supposing that each edge has weight 1, but in this shortest or longest path, here we are supposing maybe that each edge can have different weights, which nodes certainly appear in any path. That is, we can also do this. We can also do this. We can do this. I think for this, we can first of all find out how many paths there are, and we can also keep track of how many times a certain edge or node is being used in any path. And for nodes which are being used the same number of times that there are paths, that means those nodes are being used every time for any path. So yep, these nodes will be certainly in any path that we go through. Counting the number of paths. Okay, how do we count the number of paths? Let's write an algorithm for this. Write in this static int count paths, takes in start, takes in end. Let's Here we can give big names instead of this. Yeah, parent and start and end. We can give big names. How Python VM works or JVM, for instance. Yeah, I mean, calling it a VM is more of a like compliment. Did you go? No, not yet. What you're describing or thinking for virtual machine would be made using pure logic gates, which I wanted to implement. You wanted to implement pure logic gates, that is work. Okay, count paths, returns an integer, algorithms, count paths, take in start and end, and also like of course the adjacency list. Adjacent list. Okay, we have start and end and our adjacency list. We will use DFS. Now we already have one DFS algorithm in our class, but this is different. We are doing DFS, but like concerns are different. So we will have to write a different DFS for this one and this one for counting paths, for counting number of paths. For counting number of paths, what would we like to have? Just an integer, just an integer. The question that we will be asking through our DFS journey is going to be, when we call DFS on a specific node, how many different paths go from this particular node to the final, like to the final target end node that we are looking for. And what do we know beforehand? What we know beforehand is, when we are at the end node, there is only one way to get from the end node to the end node. That is, don't go anywhere. Just that. Yep. And let's say for something like this, if we look at how many different ways there are to get from 1 to 6, let's say, we will call our answer would be DFS on 2 plus DFS on 4. For DFS on 2, we will call DFS on 5 plus DFS on 3. For DFS on 3, we will call DFS on 6, which already is the end node. So this will return 1. And the value for this thing would be the sum of all the DFS which are being called by this function. So answer for 3 would be there is only one path to get from 3 to 6. And then for 2, answer would be 1 because 3 is the only child of 1 and 3 has a value of 1, so 2 will also have a value of 1. And for 5, 5 calls on for 2 and 3. 2 has a value of 1 and 3 has a value of 1. So 5 will have a value of 2, 1 plus 1, 2. And then 4 will have a value of 2 because 4 is a parent of 5. And 1 will have a value of 1 from 2 plus 2 from 4 and total would be 3. So there are in total 3 paths to get from 1 to 6. Makes sense? Let's see. Static and DFS count path stakes in the current node and vector into ADJ and visited nope vector of integer counts, and we are not defining the thing here right now. We will define it here. What will this do? This will call the DFS on the starting node. Just that. So yeah. So shit, this function is not even doing anything. This is just like a wrapper around the DFS function. No shit, this is actually doing something. Count maybe the 5 0 initially. Every count is 0, and this also needs a visited node. Visited. I think we cannot use a single visited node for everything because these functions are static. Visited ADK dot size and false. Yep, and call DFS. This is DFS count paths. Current is start and shit. We also need to pass in the end node here. How would the DFS know what is the end node? Return the response later on. Yep. And algorithms, DFS, count paths. Res equals 1 and for in x every node that is connected to res and that is connected to the current node, or even before that, if current equals the end node, then return 1 and not just yes, visited also needs to be passed on. Reference visited vector of bool reference visited. Yep, before returning, but visited n equals true. It doesn't even matter, but okay. And counts for n equals 1. Then return 1. Else we do more. Okay. Nope. Before that, I want the full ecosystem to be able to run on it. A 16-bit processor which do logic, which do use logic gate and the ABI binary interface, application binary interface. It is used in writing this. So this kind of small part in the big project I was okay. Like I will have to read the C code to understand. Yes, I will read it today. Okay. In our DFS for int x, abj, I, and x. Boolean is not set. That is good. Every node that is connected to I. What is I? Nice question. Current node if no int res equals 0 and does not matter if it is visited or not. Yep, shade. I think we don't even need visited. Yes, shade. We don't even need visited vector. We can just have that information in our counts vector. Yes, we can just have that information in our counts vector. And we can say initially count for everything is -1. -1 means not visited, 0 means anything else means this, the number of ways to get to the end node. So here, if counts for x is equals -1, then call DFS on x. Paths with current node being the x node and end node being the end node, ADJ being ADJ, and counts being counts. Cool. And let's plus equals whatever is returned by this. And counts for x would also be updated. Count for x would also be updated by this. And if it is not -1, then let's plus equals counts x. And here counts current equals res and return res. That should be k. Algorithms count paths. Let's use this. Algorithms count paths. Count paths. This statement is start. Let's use 4. N is 6 and then UDJ with a new line. Let's see how many paths there are. 3. 3 in this one. 3 ways to get from 4 to 6, which is correct. One is from this way. Other would be 4, 5, 2, 3, 6, and the last would be 4, 5, 3, 6. So that is cool. Counting the number of paths. There are a total of 3 such paths in this one. The paths x denotes the number of paths from node 1 to x. Okay. As a base case, paths 1 equals 1. Yes. Then to calculate the other values. Okay, they have a different system here. We have our starting and ending node fixed and our paths or this count variable, our counts variable is telling us the number of wait, ways to get to end from let's say count I means ways to get to and from I. No. So there is a difference between the logic, but the end is the same thing. Yep, paths of the current node equals paths of every child that it has, or maybe parent in this case. This is parent. Let paths x, yep. And then to calculate other values of paths x, we may use the recursion this, where a1 to ak are the nodes from which there is an edge to x, which means parents of x. Since the graph is acyclic, the values of path x can be calculated in the order of a topological sort from the end back. A topological sort for the above graph is as follows, like this, as the number of paths are as follows. Wait, we can use topological sort here. Yes, we should use topological sort here because when we are finding answer for a node, we must know the answer for its parents, which means this node x should come after all of its parents, which is just the definition for a topological sort. For example, to calculate the value of path 3, for path 3, we need to know the answer for its parents, 2 and 5. We can use the formula paths 2 plus paths 5. And for 2 and 5, for 5, we just need to know the answer for 4. And for 2, we need to know the answer for 1. And for 4, we need to find the answer for 1, for which we already have the answer. It is 1. Yep. And extending the Scrooge algorithm, like someone said here, extended the Scrooge algorithm. Let's see. A byproduct of the Scrooge algorithm is a directed acyclic graph that indicates for each node of the wait, this is exactly in the Scrooge algorithm we are finding the shortest path from every node to the end node. Can we also find out the total number of paths from a starting node to every other node? I think we can. A cyclic graph that indicates for each node of the original graph possible ways to reach the node using a shortest path. Dynamic programming can be applied to that graph. For example, in this example, the shortest paths from node 1 may use the following edges. Wait, a byproduct of this class algorithm is a directed acyclic graph. Shit, this class algorithm works on unidirectional graph, right? Bidirectional graph, and as a result, it gives us a directional graph where if does not matter which node or edge we take, we are always going through the shortest path to get to the other nodes. So as a result of this class algorithm, we get a directed acyclic graph that indicates for each node of the original graph the possible ways to reach the node using a shortest path from the starting node. Dynamic programming can be applied to that graph. For example, the graph this, if we apply this cross algorithm, we get something like this. Shortest path from node 1 may use the following edges. No matter which edge we take, we are going through the shortest path. Now we can, for example, calculate the number of short ways from node 1 to 5, which will be 2, which is 2. Directly we can go, wait, 5 is this, shit. Okay, so from 2 5, there are multiple ways. 1 to 2 to 4, then to 5, and the path cost would be 8, and the other way is to 1 to 4 to 3 to 4, and 1 to 2 to 3 to 4 to 5. 1 2 3 4 5, shit. And there also the cost is 7 8, and the other is 1 3 4 6, and the cost is 8. 1 plus 2 plus 5 8. Okay, representing problem as graphs. Okay, we have moved forward. And then we have successor paths. Okay. Okay, what have we seen till now? Dynamic programming, number of ways, what is topological sort, how to apply topological sort. It is fine, cool. And dynamic programming, using dynamic programming, we can find out a bunch of things about a path. That is also cool. About a graph, we can extend these graphs algorithm to our use cases, which is, yep, if we understand how this works, we can tinker with the base algorithm and the concept of representing problems as graphs. Cool. Actually, any dynamic programming problem can be represented as a directed acyclic graph. In such a graph, each node corresponds to a dynamic programming state, and the edges indicate how the state depends on each other. Yes, we can do this. This was in the book, the algorithms book. Hello, I started doing coding from 650x. It's kind of overwhelming, I feel like. No? I mean, yes, that is how you do feel. When I was also doing CS50, I felt like shit, I can never do this thing. But yeah, CS50 now seems much easier than it did at the first time. And yeah, just like keep at it. You will get better with time. CS50 is, by the way, quite challenging for someone who is new to programming itself. So yes, and that is why I think it is also good. And the teacher is also pretty cool. He explains things very clearly, and he makes it feel like the mistakes that you are making, they are normal, and you are not just too dumb that you are making those mistakes. Like, I think when I started programming in C, I wrote, we like generally write include std io.h, and I wrote a studio.h, and I thought why my code is not working. And someone in the crowd, in like where the CS50 lecture was being recorded, someone asked him, David Milan, like his code is not working, and he said change studio to stdio. And yeah, it was just cool. Yeah, you are not dumb, you are just like new to this. And okay, we know any problem can be converted into a dynamic programming problem. How do we know that? We know that from Introduction to Algorithms PDF, this book. Shit. The same link, literally the same link. Introduction to Algorithms, DW, dgw2.pdf. Should that is not the book. Yeah, but in this book, Introduction to Algorithms, in the dynamic programming section, they do say that they do represent a dynamic programming solution as a directed acyclic graph. So yes, we can convert any dynamic programming problem into a graph. As an example, consider the problem of forming a sum of money n using C1 to Ck coins. In this problem, we can construct a graph where each node corresponds to a sum of money. Each node corresponds to a sum of money, and edges show how coins can be chosen. For example, for the coins 1, 3, 4, and n equals 6, when we want money 6, and the coins that we do have are these. The graph is as follows. When we have 0 money, we can have a sum of 1 by choosing a coin of 1, and we can have a sum of 2 by going from 1 to 2 by choosing a coin 1. So we can imagine this as if numbers were written on the edges, which are indicating which coin we are choosing. So we can think that over this edge we have written 1. So when we take money 1, coin of value 1, at a value of 0 we get 1, then we again take 1, we get to 2, and we again take 1, we get to 3, 4, 5, and 6. Or we can take 3 directly, and from 0, if we were to take 3 using this edge, we would get to 3, and then we can take another 3 and we can get to 6. So these edges represent the choices and the nodes represent the current state. So that is cool. And we can just find out what is the shortest path from 0 to 6. That is also cool. That would be finding the solution for problem. Using this representation, the shortest path from node 0 to n corresponds to a solution with the minimum number of coins. Yes, because we are making least number of choices. And the total number of paths from node 0 to n equals the total number of ways to reach from 0 to n equals the total number of solutions. Now, successor paths. Successor paths where each node only has a single outgoing node. The out degree of each node is 1. Yep. So one node points to only one other node and not to multiple like here. So what are the properties of such a graph? Successor paths. For the rest of the chapter, okay, we will focus on a successor graph. In those graphs, the out degree of each node is 1. That is exactly one edge starts at each node. A successor graph consists of one or more components, which of each contain one cycle, k, and some path. Wait, why do they contain cycles? Is this like a required property? Shit, yes, they will contain cycle. Yes, they will always contain cycle. They will always contain cycle. Why? Let's say we have 4 nodes, and in a successor path, each node must be pointing to some other node. So let's say this node points to some random this node, let's say, and this points to this, and this one points to, let's say, this one. Now this node which is left, and this is the only one which does not point to any other node. Which other node should this point to so that there is no cycle? If this node were to point to this, then we have a cycle. Our cycle is this, and this. If this node were to point to this, then we have a like direct cycle from here to here, and this points to this. And if this node were to point to this, then again we have a direct cycle here and here. And also we can use to like justify or prove why there must be a cycle in a successor graph. We can use the concept of a tree. In a tree, if there are n edges, n nodes, then the number of edges is n minus 1. And we know that if we increase one edge in a tree, we will get a cycle. In a tree, if we increase the number of edges from n minus 1 to n or anything that is greater than or equal to n, if the number of edges is greater than equal to n, we have a cycle. We have a cycle. And in a successor graph, since each node has an edge that points outside to some other node, there are going to be at least n number of edges. The number of edges is going to be at least n. And since n, if there are n edges, we have a cycle in our graph. Therefore, this successor graph is going to have a cycle always. Okay, that is cool. It's cool. It's like, yes, makes sense. Okay. A successor graph consists of one or more components, each of which contains one cycle and some paths that lead to it. It is the cycle. Successor graphs are sometimes called functional graphs. Functional graphs. Okay, why? The reason for that is that any successor graph corresponds to a function that defines the edges of the graph. The parameter for the function is a node of the graph, and the function gives the successor for that node. Okay, that makes sense. That makes sense. We can think of, yes, since each node only points to one other singular node, we can think of this as a function which takes some node n, some nth node, and whatever the output is, let's say n dash node, this output is the node that this nth node points to, and that is how a function is defined. If you give one input, it always gives you the same output. Nothing changes the behavior of the function. So that is cool. We can think of this as a function graph, functional graph, and the function gives the successor of that node, and the function gives the successor of that node. Yes, we give in the current node and we get the output node. 1 points to 2, 1 points to 2, defines the following graph. Yep, cool. Since each node of a successor graph has a unique successor, we can also define a function success xk. What would be the successor of x if we go forward k amounts? That gives the node that we will reach if we begin at x and walk k steps forward. For example, for k equals 0, we will get x, and for k equals 1, we will get the successor of x. And for example, in the above graph, if we were to call this function with 4 and 6, with 4 and 6, so we want to move forward 6 steps starting from node 4. Where will we be? We start here, we move 1 step, 2 step, 3 steps, 4, 5 and 6. We end up at 2 because we will reach node 2 by walking 6 steps. Cool. A straightforward way to calculate a value for this thing, straightforward, would be to just literally move k steps, is to start at node x and walk k steps forward, which takes O of k time. But we can reduce this by pre-processing some values. However, using pre-processing, any value of success x and k we can calculate in only O of k time. Yes, we can do that, I guess. And hello, Kakashi. And shit, do you remember we were like at some point we were talking about kth ancestor or binary lifting? I think that is what will be used here. Binary lifting or kth ancestor, but not ancestor. This is in the like reverse direction. Successor, not ancestor. But yeah, same concept. The idea is to pre-calculate all values of success x k, where k is a power of 2, at most u, where u is the maximum number of steps we will ever walk. U is the, yes, and yep, and then the answer, for example, since we have calculated f for every node from 1 to nth node, and the steps for which we have calculated this are 0, 1, 2, 4, dot 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 till like 2 power 30, something like that. Since we have all this information beforehand, and if we are looking for answer 15, let's say, If we move forward 15 steps in starting from 2 node, then the biggest answer that we know the answer to, which is smaller than or equal to 15, is 2, 8. So answer for this we can write as 215 equals 2 comma 8, and whatever is the output of this thing, and shit, we cannot just write it like this, whatever is the output of this from this node, whatever it returns, let's say this gives us x, we have to move forward 7 steps. We have already moved 8 steps, we wanted to move 15 in total, so move 7 steps from x forward. But we don't know the answer for 7. What we do know is if x 4, 4 is a power of 2, so answer for this is going to be, call this function, and whatever the return value of this is, if it is y, and call f y, and out of 7 we have moved 4 steps, we have 3 more steps to move, but we don't know the answer for this, so we will find answer for the biggest power of 2, which is 2, and whatever is returned by this, let's say it is x, z is returned, then if z move forward 1 step, because we wanted to move 3, we have moved 2 steps, we want to move 1 step, for which we do know the answer, and that is the final answer. So shit, if we were to write this in a single equation, f 215 equals, this is the final function call, f move forward 1 step, this z is the output of this, f y is the output of this, f, and this takes in x is the output of this, 2 8, so call 2 comma 8, 2 comma 8, whatever the this was supposed to be x, we call x with 4, so 4, it would be better to do a little bit of syntax highlighting here, but okay, and okay, we have x, and this thing will return y, we call y with 2, this thing returns z, we call z with a step of 1, and that is our final answer. Let's do a little bit of syntax highlighting here so this looks better. One, and inner function f being called with 2, yep, and the inner function is f being called with 4, and the last function f to 8. That is how we can find out the kth successor or ancestor. And hello, cracked roaster prism problem. Yep, we will do that. Got late today. Shit, missed out already. When you start streaming, I started at 12. No, 12:30. My bad. More time for such extra activities. Weekends alone don't cut it out. Wait, what do you mean? Like, huh? What is YouTube UI changed? Your video is showing smaller and the chat panel is wider. How do I fix? I don't know. They made it wider and not recognizable. What shitty UI? Maybe we can. You can send a pull request, right? Fix it. He can do this. Crack do a step. He does these things. He can fix it. k and straightforward way. Yep. Well, yeah, we have the theory down. So do we want to like actually write this out? Kth common ancestor. I want to see what Ericto said about this. Ericto courses. And yes, he has like two channels, Ericto normal algorithms, and then the other one, Ericto hard algorithms, and it says power square. Binary lifting is lowest common ancestor. That is different than kth ancestor of a tree node. Yes, lowest common ancestor is different from this. And this is somehow similar to how sparse table works. Yes, this is similar to how sparse table works. Sparse table is cool. Sparse table is cool. Actually good. Because using sparse table, we can find out multiple things. Using a sparse, using, okay, if we want to find out if our problem is to answer queries where we want to find out the sum between some specific range x and y, we can have a prefix. Like prefix works where prefix I is the sum of range 0 to I, sum of all elements in 0 to I. But what if we want to find the minimum for a specific range? That is our query. What is the minimum in range x to y? We cannot have a prefix because if our vector looks like this 1 2 3 4, and like using a prefix would not even make sense. Our prefix vector would look like 0 0 0 0 all the way till the end, because in the in this range 0 is the smallest, and in this R range for this prefix always starts at this point, and here 0 is the biggest one. So yeah, prefix does not cut out when we want to find out the minimum or the maximum. We can use sparse tables, which are better, and sparse tables are two-dimensional, where we have I and some, let's say, P, and this thing SP IP is equal to the minimum or maximum or sum or whatever our sparse table is storing. Let's say minimum in the range I included, and I plus 2 power P. And using this we can calculate the answer for any range x to y, and this is just cool. This is just cool. Fix it, make it 75 25. Wait, that is bad. I think you can do something like reduce the zoom. Maybe that might work. I don't know. Can you give me context what you're talking about? Shit, bro, wrote the problem here. If you see a stream or video, there is a video on the left, and then chat panel recommended video on right. Today the update, I guess, so chat panel is viral, like currently 35 to 40% of the screen. That is not good. Okay, a straightforward way to calculate a value of success x to k is to start, yes, like this will take k time. The idea is to pre-calculate all values of success x k, where k is a power of 2, like a sparse table, and at most u, where u is the maximum number of steps we will ever walk. Yes, this can be efficiently done because we can use the following recursion. If k equals 1, then answer success k. Otherwise, if k is greater than 1, then success move k by 2. Wait, shit. K by 2 steps, and pre-calculating the value takes O log U time, because log U values are calculated for each node in the above graph. The first values are as follows. Yep. But why are they doing k divided by 2? K divided by 2 does not make sense. Like, one of them has to be upper limit and the other one has to be lower limit. By default, k by 2 would be lower, so we have to make the other one upper limit so that their sum is equal to the original k. Right, we want k equals k by 2 plus k by 2. We want to move forward k steps, but this is not true in C or C++. For something like, if k equals 7, then k by 2 equals 3, and 3 plus 3 is 6, which is not 7. So we have to take one as the lower limit and the other as the upper limit, so that for k equals 7, when we do 7 by 3, if we take the upper limit, we will get 4, and for the lower limit, we get 3, and their sum is equal to 7. So yeah, but I guess this is just like a recommendation, not how they are actually implementing the algorithm. Calculated for each node in the above graph, the first values are as follows. After this, any value of success xk can be calculated by presenting the number of steps k as a sum of powers of 2. For example, if you want to calculate the success value of success 11, yes, we also did something like this here, like 8 plus 4 plus 2 plus 1 to get to 15. They skipped 4 because 15 minus 4 is 11, which is what they are finding the answer for. For example, in the previous graph, success 11, 411 would be equal to this, and answer would be 5. Such a representation always consists of log k parts. So calculating a value of success xk takes log k time, which is much better than k time, which would be the naive algorithm. And now cycle detection. We can use the same, we can use what we have written already for cycle detection. This algorithm is cyclic graph where each node has 3 states. Well, if you want more video with, you can choose the live chat window. Then how will I treat actually only full screen as a fixed even closing chat? Shit, bro is suffering, actually suffering. Cycle detection, not detention. Consider a successor graph. Okay, shit. We are talking about cycle detection in a successor graph. We already know that a cycle exists in a successor graph, but we want to find out where it is. Yes, where it is. In a successor graph, we can like think of it as one big cycle, and there are like other things connected to each other in some way. We want to find out the parts of this cycle. Yes, for which we can just start our DFS at any node, and the first node that we visit twice would be a part of the cycle, and then we can run our DFS or BFS on that node, and all the nodes that we can go to from that node would be a part of the cycle. Yes, would be a part of the cycle. So this takes in 2 DFS. Okay, let's write an algorithm that takes in like this successor graph and gives us a vector listing all the nodes which are in the cycle. Floyd Warshall, shit, Mr. Floyd didn't like collaborate with Mr. Warshall on this one. And then we have strong connectivity. Okay, this is the last thing in this chapter. That is cool, quick enough. Real-time debugging. Uh, theater mode is cool. Theater mode is cool. Okay. Mm, we need a function that takes in successor graph and gives a vector of int successor graph cycle. Just that this takes in the adjacency list and vector int algorithms cycle and yep, vector adj, and there would be two steps: finding out which node is a part of the, but shit, there will be multiple cycles if there are multiple components. Let's ignore that fact. We'll just assume that there is only a single cycle, or we are just going to return a single cycle from the whole graph. We need to run DFS. This will have its own DFS. Successor graph cycle, and this will not return this. This will return an integer, which would be -1 if there is no cycle at the end of this graph. No. Yep, which node is a part of the cycle if we go forward with this node. Yep. Okay. The question being asked by the DFS would be, for this node, if we move forward on this, which node is a part of a cycle, which would call DFS on this, 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 which would call DFS on this. But when we are here, we will say that shit, we already have seen this node before. So this will be returned by this to this, which will return it back to 4, which will in turn do the same to 3, to 2, and 1 will give us the answer. Okay, so we need a visited vector. Size would be, everything is false initially, and I equals cycle node as why are there like two methods? Current is 1. Okay, or instead of fixing this to 1, we can ask the user for the node. Int cycle node. This will give us which node is creating the cycle, which node is a part of the cycle, and every node that is reachable from that node would be a part of the cycle. Okay, so we just have to do a DFS, which we can do right now here. Yep. Okay, int C node, parent node is cycle node, and not cycle node, but the node that the cycle node is connected to, which is ADJ cycle node. And here we will say method in response, uh, like the first node that this is connected to, even though this is only connected to a single node. In which case, since we know that this is a successor graph, we don't even need an integer here. If every node is only connected to one other node, so we can just use a vector. Which means nothing. Which means we don't need a separate DFS function. We can do this in-house. Right, we are currently at node. Everything is false. Everything is false here. While visited for node is not is false. Node equals node. Yes, node equals node. Right. While it is false, then visited for this node equals true, and new node becomes existentialist node, the node that this node points to. Yep, we will then have the cyclic nodes, and int current node would be equal to the next node. Yes, the next node, which is ADJ node. Yep, and vector r response add node, while C node is not equal to node. What we will do is we will add this current node as well, push back C node, and we will move forward to the next node. C node is ADJ, that's current node, and at the end return the response. That is good enough, and that should also work. Algorithms, successor graph cycle, give us the cycle. Solve this with the ADJ with 1. What is ADJ? Shit. Okay, we also have to change this. Okay, but the ADJ 0th node does not point to anything. Invalid operands, binary vector type T. Let's no, I didn't do anything. I didn't do anything. That is not my mistake. Uh, yes, the stream settings are same as they usually are. Node 1 points to 2 to 3, 4, 5, 6, 6 points back to 4. 1 points to 2, 2 to 3, 4, 5, 5 points to 6, and 6 points to 4. Successor graph cycle. What is the problem with this? Successor graph cycle returns vector of an integer which is being printed later on. Invalid operands, binary expansion. Output is stream is being taken here. It persists. Algorithm successor graph, give it ABJ. Okay, now it works, but it wouldn't work directly. We should see 4, 5, 6, something like that. 4, 5, 6. If we were to change this and say that 6 points to 2, and we started for our looking from node 3, then we should get 3, 4, 5, 6, 2. So 6 points to 2, and we started looking from 3, 3, 4, 5, 6, 2. Probably 3, 4, 5, 6, 2. Cool. Yeah, like that is kind of it. Uh, a simple way to detect the cycle is to walk in the graph and keep track of all the nodes that have been visited. Once a node is visited for the second time, we can conclude that the node is the first in the cycle. This means this method works in O of n time and also uses O of n memory to keep track of all the nodes which have been visited. However, there are better algorithms for cycle. Shit, there are better algorithms. The time complexity for such algorithm is still O(n), but they only use constant memory. This is an important improvement if n is large. Next, we will discuss Floyd's algorithm that achieves these properties. Okay, they are saying that we can reduce the amount of space. We cannot reduce the amount of time, but we can reduce the amount of space. They are saying we don't have to use a visited array. We can use something else. Okay. Can we reach that conclusion? Like what thing they are going to use? I don't know. Let's see what they are doing. Mr. Floyd. Shit, Floyd Mayweather was a boxer. Shit. Okay. Uh, graph using two pointers. They are going to use a method or mode or technique which is used for finding out if there are any cycles in our linked list. Yes, in a linked list, if we want to find out if there are any cycles, we have two pointers. one pointer, pointer number 2, and the random pointer. Remove that. And one of these pointers moves slowly, one by one, and the other moves fast. Other moves fast, like by 2 steps or 3 steps. And after moving them at every turn, we check if they are pointing to the same thing. If they are pointing to the same thing, that means there is a cycle in the linked list. And yep, it means that there is a cycle in the linked list. And the node that they are pointing to is a part of that cycle, because we reached that thing like multiple number of times. Okay, walks forward using 2 pointers A and B. Let's implement this. So in this part, we are finding out the node. You will have a different thing. Okay, A is node and B is also node initially. So while A will, let's like increase A by 2, or yeah, let's increase B. ADJ node, the next node, yeah, while A is not equal to B. And when it is, we will say node equals X. Right, while A is not equal to B, A will keep moving by 1 step. So A goes to the next node, ADJ, and B will go to the next node, ADJ of the next node. Next node would be ADJ. ADJB is the like legit next node, and we are going to the next of that node. We can increase the number of steps here actually. Let's see if this works. It works. 5, 6, 2, 3, 4. We cannot say which order we will get these nodes in, but we will get the nodes. 5, 6, 2, 3, 4 is a cycle. 5, 6, 2, 3, 4, because we moved this edge from 4 to 2, 6 pointing to 2. So that is correct and pretty cool. But will the time complexity be the same? Okay, both nodes begin at node X, that is the starting node of the graph. Then on each turn, the pointer A walks 1 step forward and the pointer B walks 2 steps forward. The process continues until the pointers meet each other. Yep, yep. At this point, the pointer A has walked k steps and the pointer B has walked 2k steps. So the length of the cycle divides k. Length of the cycle divides k. Thus, the first node that belongs to the cycle can be found by moving the A pointer to node X and advancing the pointers step by step until they meet again. Wait, the pointer has moved k steps and the pointer B has moved 2k. Thus, the first node that belongs to the cycle can be found by moving the pointer A to the node X and advancing the pointers step by step until they meet again. A equals X. Step by step, A is also moving, B is also moving. First equals A. Okay, that does not make sense. At this point, the pointer A has walked k steps and the pointer B has walked 2k steps, right? Whatever k is. So the length of the cycle divides k. If we started at a node which is a part of the cycle, thus the first node that belongs to the cycle can be found by moving the pointer A to node X. Why are they moving step by step here? Okay, shit, makes sense. I think we move A back to our starting X node, and yes, we keep moving them forward one by one step. First equals A. Okay, after this, the length of the cycle can be calculated as follows. Length equals 1, B equals successor of A. While B does not come back, we'll keep increasing the length. Okay, that is cool. That is cool having two pointers which move forward. That is cool. And I guess like there is nothing else to do today, nothing that I want to do. Mm. Wow, how much have we done in this graphs section? Graph algorithms, we have done like basics of graphs, graph traversal, shortest path, tree algorithms, spanning trees, directed graphs. Next would be strong connectivity, then tree queries, then path and circuits. Camera is going to die. Okay, there are like 4 things left, just 4 more things, and it is going to be cool. We did do shortest paths at some point, this graph. That was cool. Yep, and that would be it for today. We did directed graphs, what is topological sorting, which was simple enough, how we can use dynamic programming in a directed graph to find out multiple things like the number of paths from a starting node to any end node, or the length of the minimum or the shortest or the longest path, successor paths, what are successor graphs, and cycle detection in a successor graph. Yep, and why there is a cycle always in a successor path. And that would be it for today. And thank you for being here. Bye.